Alright, so today we are doing the limit comparison test. If you're watching this, you probably already know what this is about. It's about checking to see when a series is convergent or divergent. So here we go. We'll start off with the main idea. Limit comparison test involves two simple steps. Step one will be to try to figure out what a series smells like. Sometimes you can just look at it and sniff it, and you'll know if it smells like something or something else or whatever. For example, this one, what do you suppose it smells like? You can see the n to the third is, as n's grow large, is very much a dominating term, while the 21 becomes kind of insignificant. No, it really becomes insignificant as your n's grow large, and there's nothing special about 21. The same thing could be said if you were to change it up to maybe 5. Well, it would still be just as insignificant. And so you start to get the idea that when you look at a series, you try to sniff out the best parts, the most important parts, and you try to ignore the less important things. It could be pi, 21. It really wouldn't matter. At the end of the day, you could say this one really smells a lot like 1 over n to the third. That's your first step. First step is to look at the series and try to figure out what's important and what's not important. In this case, we feel that the series, or any variation of it, like or any other constants here, would still smell like 1 over n to the third. That's the first step. But of course, as any good smeller knows to do, after you smell something, then you've got to verify that your smell is good. It's not lying to you, so you got to taste it. That's the second step, the verification step. And that would go something like this. To confirm your smell, you need to check this famous limit. The limit of the sequence that you've got, and you take that as a ratio of the one that you think it smells like. And if these two are roughly the same, when you divide one by the other, they should give you some sort of constant. Otherwise, they wouldn't be the same. In other words, here, if this was true, if so, then you could say, well, an over bn is roughly the same as k, at least for large n's. That's what this limit says. And that says, well, it must be that an is roughly the same as k times bn, just by multiplying both sides by bn. And under some good conditions, you can actually say, you know what, I'll just slap an infinite sum on both sides. An infinite sum as n goes from 1 to infinity. An infinite sum of k, bn as n runs from 1 to infinity, and say, you know what, these two are probably the same. They either both converge or both diverge. They might be differ only by constant. That would be ideal. This is the taste test. The taste test is exactly to do this. To check this limit to see if the ratio is really a constant. That has a domino effect. It forces you to think this way, that way, and under some conditions you can slap this sum on both sides and declare them really confirm your smell taste, your sense of smell here, that they were really doing the same thing. They were acting the same way. All right, let's formalize that. Let's maybe more formalize it with some nice writing. So we said that excuse me. So we say that this will force an to be roughly k times bn for large n's, and under some conditions you can slap the sum on both sides, and that forces the two series to be the same. In our example, we had sniffed out this one and we said it probably smells like this one. Now we just need to verify, confirm. Let's do the second step, the confirmation step. So to do that, we take a look at this limit. That would be the limit of the first one. This one was our an's, and this one was our bn's. We looked at this one and we said it smells like that one. And so we look at the ratio here. These are your an's and this is your bn's. And what we'd like to get out of this would be a constant, some number. I don't care what it is, 5, 7, 12. I don't really care what this number ends up being. -3. It doesn't matter. If it's just some non-zero constant, then these two will behave the same. They will both converge or both diverge. Clear? Alright, let's clear this up and continue. So we're working on this limit, and you can do a little bit of algebra here. Maybe flip this to the top and then move these to the bottom. Whatever your algebra skills should be good. That gives you something like this. After a little flipping, then you can try the plug-in method, but this will give you infinity over infinity. So we rewrite by dividing out by the dominating term, n to the third and n to the third. That would divide this by n to the third, that by n to the third. So it would look kind of like this. Divide this by n to the third, divide this by n to the third, divide this by n to the third. And if you do that, it would turn, of course, into this. It would turn into this. And then that, of course, turns into 1, because as n goes towards infinity, this goes to 0, this becomes 1. And so you're done with the limit. The limit is equal to 1. That confirms that the taste test, right? We wanted to confirm that this limit is equal to some constant. In this case, the constant turned out to be a 1 down here. And so now we can declare under some good conditions. Maybe I could tell you just what the conditions are. The conditions are that, let me say what the conditions should be. The conditions are that one of these, at least the AN or the BN, at least one of them, should have positive terms. I'll write that formally in just 2 seconds. Those are the conditions here. One of these should be either the ANs or the BNs should just be positive, not oscillating. Some bad things can happen when you have both oscillating signs, plus minus, or some variation of that. So if we can just keep one of them positive, everything will be good, and you can slap the sum on both sides. Once you confirm your taste, your smell, sense of smell here, that the constant is 1, you can declare, you know what, the two series are the same. So formally, here we go. Let's go back a little bit. So once you get to this and say this confirms it. This confirms that they really do behave the same, and then you can say, well, this one clearly converges. Why does it converge? Well, for example, by the integral test, it would converge, or just because it's famous. This is called P series. Whenever that number is bigger than 1, and you have n, just a plain old n here to some constant number, you just, hopefully you've done a whole bunch of these integral tests, you can recognize these immediately. If this number is larger than 1, you can just say it converges by the integral test. Or do it if you haven't done it. Alright, so formally, let's take a look at what we just, summarize what we just said. Here's how the, here's how the limit comparison test works. So you first check, you first have to smell it out and figure out what does it smell like, and then you do look at this ratio, the one you have and the one you think it smells like, and you check that limit is a constant, a non-zero real number constant k. Okay, and then you just check to make sure nothing bad's going to happen, so you can slap sums on both sides. At least one of them should be positive. Either the numerator sequences should be positive, or the denominator sequences should be positive. Once you check these two things, then you're good to go. Then you can just say, well, then the two series behave the same. Either they both converge or both diverge. They're off only by a constant. Okay, that's a summary of the limit comparison test. That's the main idea. Come back for some nice examples. See you guys here next time. Peace.